In our last discussion, we looked at the mechanistic theories of aging, and in this one and the next discussion, we will be looking at the evolutionary theories of aging. But before we go there, I need to remind you of the proximal ultimate dichotomy that we talked about in the first week of our discussion. So, just to remind you, suppose there is a dead body lying, then you can ask two kinds of questions in that context. One is, how did the person die? Was it due to a bullet injury or a knife injury or whatever? This is the kind of question that the forensic expert is going to ask. And the other thing is about, what is the reason for the person's death? What is the motive? And this is the question that the investigating officer is going to ask. So, in biology, these two kinds of questions, these are known as the proximal and the ultimate kinds of questions, and the evolutionary explanations, they are of the ultimate type. So, this is pretty much what is happening in the context of the aging theories that we are looking at. So, the mechanistic and the evolutionary theories, they are not really antagonistic to each other. It is not that if one of them is true, the other has to be untrue. No. The mechanistic theories are essentially trying to figure out the proximal causes of aging, whereas the evolutionary theories are trying to figure out the ultimate cause of aging. In other words, the evolutionary theories are primarily asking what is the reason for which organisms have not been able to get rid of aging, whereas the mechanistic theories are asking, okay, at the levels of the molecules, which molecule is going up, which molecule is going down, which molecule is causing some wear and tear, because of which we are getting the symptoms of aging or the negative effects of aging, right. So, this needs to be looked at explicitly in this context, that the two sets of theories, the mechanistic and the evolutionary, they are not really antagonistic to each other. Now, as I told you that this particular question as to why evolution has not been able to take care of aging over billions of years, this has been around for a very long time. And the earliest evolutionary explanations for aging actually can date back to this Roman poet Lucretius, who ended up saying, I am not quoting him, this is just a paraphrase. He said that there might even be a benefit to aging and death, and the benefit is that they end up paving the way for the upcoming generation. In other words, if the organisms die, only then will the resources get freed up for the younger generation. So, this is something that was put in very nice words by Alfred Russel Wallace, the same Darwin Wallace. And what Wallace said, I am going to give you a quote. He said that, "For it is evident that when one or more individuals have provided a sufficient number of successors, they themselves as consumer of nourishment in a constantly increasing degree are an injury to those successors." In other words, when the parents have produced enough number of babies, then both the parents and the babies are utilizing the resources, they are in some sense competing for the resources, and in that case the presence of the parents can be harmful for the babies. And therefore, natural selection therefore weeds them out, them as in the parents, and in many cases favors such races as die almost immediately after they have left successors. In other words, once your evolutionary job is done, as by producing the babies, then it is better for the parents to die. That is roughly speaking what Wallace was talking about, and he thought that if there is a mechanism like that, then natural selection is going to favor that mechanism in a big way. That is what he means by saying natural selection weeds them out. Now, this particular idea leads to the concept that death and aging leading to death, this can be a programmed feature of organisms, and this idea was put forward most strongly by this gentleman. Again, you have met him earlier, August Weismann. This is the person who was cutting off the tails of rats to show that acquired characters are not being inherited. So, he actually made multiple contributions to the field of biology. This is one of his more famous ones. So, he thought that perhaps organisms are programmed to die, and this is an adaptation which is favored by natural selection to eliminate the old and therefore worn out members of a population. So, some people have joked that when Weismann was around, he was a German. So, when Weismann was around in German academia, people had to wait for the professors to die before their positions were taken up by younger people. And some people have joked that maybe Weismann was actually thinking about that aspect of academia when he wrote about this, but this is just a joke, nothing else. So, the mechanism that Weismann proposed was as follows. This is very interesting. Look at it. This is the quotation. Lifespan is connected with the number of somatic cell generations which follow after each other in the course of an individual life. Okay. So, he connects lifespan to how many somatic cell divisions are happening, and that this number, the number of somatic cell division, like the lifespan of individual generations of cells, is already determined in the embryonic cell. In other words, he is explicitly saying that the number of divisions that a cell in the body can undergo is limited. There is an upper limit to that. Now, please note that Weismann is writing this in the year 1882. At that point, and even after that point for a very long time, people actually thought that there is no end to how many times a cell can divide. However, in 1959, H. Earl Swim actually ended up showing empirically that for many kinds of cells, there might be an upper limit to the number of times the cells can divide, and in 1961 this was again put forward by Leonard Hayflick, and today we know this thing as the Hayflick limit, the fact that there is an upper limit to how many times most cells can divide. Now, of course, this guy Weismann was talking about this 70 years prior, just based on theoretical observations. So, that tells you what kind of a mind Weismann had. So, anyway, now at the face of it, this looks like a very nice argument. Okay. However, if you think about it very closely, you will realize that there are issues with this argument. What kind of issues are we talking about? The primary issue is the so-called cheater argument. Now, think about it. This entire argument is saying that those organisms which die earlier and therefore leave up space for their offspring, they are the ones who are going to be favored by natural selection, because the group is being favored. So, it is a group selectionist argument. But suppose you have some mutation by which you get organisms who do not die early. What will happen? These organisms who are not dying early, they are living longer, they are going to leave behind more babies. If they are going to leave behind more babies, then obviously their fitness is greater, natural selection is going to favor them. And therefore, by the logic of natural selection, after some time, the frequency of such individuals who are doing something that is bad for the group, but is good for them, these are the cheaters, the frequency of such individuals is what is going to go up in the population. In other words, given equivalent reproductive output, the long lived individuals, they are the ones who will be favored by natural selection, and therefore, there is no mechanism by which such a thing, such a programmed death is going to be possible in any organism. Now, that is what I am saying, there is no, it is not clear how such a mechanism will sustain itself. So, this is the theoretical argument against it. However, you can still ask that, okay, fine, let us still see if it works or not. And people actually searched for quite long time, they were not able to find any such mechanism. Then they looked at data, and what they found in data was very, very interesting. Now, before you think about it, first we have to understand what is it that needs to be observed. Okay. So, if there is indeed a death mechanism, then that death mechanism means that once an organism hits a certain age, which might be different for different organisms, that is fine, but once the organism hits that age, then changes will happen in the body, because of which it will die, either very soon or over a certain period of time, whatever, but it will die. Now, if such a mechanism indeed exists, then under natural conditions, organisms most probably will need to hit that value now and then, right. Now, why is this important? This is important because under natural conditions, organisms are dying due to all kinds of reasons. Sometimes they are dying due to predators, sometimes they are dying because they did not get enough food, sometimes they die because there is a flood or there is a massive storm, during which there is a thunder strike, etc., etc. So, there are all kinds of external reasons for which organisms can die. So, many organisms will probably die before this programmed death kills them, that is okay. But the point is that at least in some cases, the organisms have to go up to their limit and be killed by the programmed death, because if that is not happening, then the organism will never require that, and therefore, there will be no selective mechanism maintaining that, right. So, that is why you expect that at least some of the organisms, particularly the ones who are living slightly longer, at least they are dying because they have hit this particular limit. Now, if this be the case, then if you look at the lifespan of organisms under natural conditions and you compare those lifespans with organisms, the same organisms when they are living under captive conditions, because under captive conditions they are provided food, there are no predators, etc., etc. So, those are benign conditions. If you compare these two things, lifespan under nature versus lifespan under captive conditions, you expect that these two will be not very different from each other. They will be slightly different obviously, because under natural conditions the deaths are going to be, there are many more ways in which you can die under natural conditions, but somewhat they should be similar. The difference between the two will not be very, very large. So, the way to observe this is to look at the lifespan of organisms under captive conditions, look at their average lifespan under natural conditions and see what kind of a difference you get there. And turns out that you actually get huge difference. In other words, under captive conditions, organisms live not a little more, but a lot more. Just to give you two examples, I mean these are just two, there are like hundreds of examples of this kind. So, this is a bird called the chaffinch, and this bird under natural conditions the mean lifespan is about 1.5 years, under captivity it can live up to 29 years. Similarly, if you look at the chimpanzee, then median lifespan, median lifespan in nature is about 8 years, under captivity the median lifespan is 23 years. And if you look at maximum lifespan, under captivity a chimpanzee can live up to 50 years. There is no known chimpanzee who has ever gone up to 50 years under natural conditions, no way, even in protected parks. So, these kind of examples straight away tell you that there is a huge difference between both the mean and the maximum lifespan under captive condition and under natural conditions, which is completely against the prediction that you are getting from the programmed cell death thing. And that is why today the programmed theory of death is not really considered very seriously. Now, this has very strong implications. What are the implications? Remember, I told you that one of the major lines of investigation all over the world right now is how to increase the lifespan and health span of individuals, of organisms, particularly humans. Now, if this programmed theory were correct and there were indeed a program, then it would have been very difficult to change that, because that is something that is part of the biology of the organism. But if you do not have a programmed death mechanism around, then that implies that it is perhaps possible to change the lifespan of organisms, in which case obviously all the work that is being done all over the world, that makes a lot of sense. So, in that context, this proving that programmed theory of death no longer works is very, very reassuring. Incidentally, Weismann himself changed his mind towards the later part of his life, looking at various kinds of data, and towards the later half of his life he actually explicitly went away from this particular programmed cell death theory, programmed death theory, and was no longer subscribing to it. Unfortunately, this change is not what people talk about. Okay? People only say that he propounded the programmed theory of death, they never said that he changed his mind. Anyway, so from this we now go to the more modern evolutionary theories of aging, and there are quite a few. We are going to look at just two of them, but these two are the most prominent ones. But before we get to understand the crux of these evolution theories, we need to revisit the definition of aging, the evolutionary definition of aging that I talked about, and we also need to look at three observations. So, if you remember, I defined evolution from an evolutionary I defined aging from an evolutionary perspective as it is characterized demographically by the increasing mortality and decreasing reproductive success with advancing adult age. Okay. So, this is what you need to remember. For aging to happen, the rate of mortality has to go up and the rate of reproduction has to go down. Okay. Why this is important will become clear in a few minutes. The other three things that we need to keep in mind is the three realities, absolute biological realities. Okay. The first thing is that if you have an organism out there in nature, then there is always a finite probability of death due to external reasons. Okay. It can be because of a predator, it can be because of a pathogen, it can be because of any natural calamity as I talked about, it can be due to any reason, it can be due to an accident, it simply while running it fell and broke its neck or whatever. But there is always a finite probability of death, which means that going from any, let us say year 10 to year 11 or year 15 to year 18, you can never say that it will definitely be able to make that passage. Okay. There will always be a small value, howsoever small, there will always be a small probability of death. The second thing is, this is very obvious, but until and unless told, people do not think about it, which is there is an asymmetric relationship between survivorship and reproduction. You can survive up to a certain age without reproducing at that age, but if you want to reproduce at a particular age, you have to first survive to that age. In other words, suppose I am talking about how many babies will I produce when I am age 30. So, in order to get to those number of babies, I first have to survive up to age 30. Without that, I cannot produce the babies. Okay. So, that is what I mean by saying reproduction at a given age is contingent upon surviving to that age. The third thing is that for any given reproductive effort, which basically means, let us say I decide to reproduce at the age of 30 or I decide to reproduce at the age of 31 or 32, whatever. For any given reproductive effort, there will always be a physiological upper limit to how many babies I can produce. Okay. Now, an organism can technically produce infinite number of babies if it lives forever, that is fine, but in a given reproductive effort at a particular year, there has to be a upper limit. And why am I saying so? That upper limit is going to be based on things like how much resource the organism can assimilate. Suppose let us say I am talking about a human, it will be decided by how many babies can be accommodated inside the mother's womb. If I am talking about an insect, it will be decided by how many eggs the female can lay or how many sperms the male is able to produce, etc. it can be a large number, but it can never be an infinite number. Okay. This is a subtle point, but if you think about it closely, you will get it that for a given reproductive effort, there has to be an upper limit to how many babies can be produced. So, now once we have these three realities and that particular definition of aging, now we are in a position to understand what exactly is the crux of the evolutionary theories of aging. And for this, what we will do is we will do a quick simulation. I will build the simulation for you from scratch, and we will do it in Excel. So, let us assume that we have an organism, and let us say, let us first do the ages. So, let us assume that we call the various age classes as x, and let us say we are measuring age in years. It does not really matter, it can be in days, minutes, seconds, whatever. So, let us call the first age class as 0. So, these are all the newborns, the babies, and then we have 1, 2, 3 and so on and so forth. So, let us pull it to some arbitrary number, say 60, whatever. Now, we assume that in this particular organism, the mortality rate going from one age class to the another stays constant. So, right at the beginning it has to be 1, because everybody has, this is the newborn class, but from the mortality rate going from 0 to 1, let us say is 0.1, some value. Okay. Again, as you will see, what value I take does not really matter, the logic that we are building, that remains the same. So, let us assume that this is 0.1 at all age classes. Now, remember we said that as per definition, aging is happening when the mortality rate is going up later in life, but here the mortality rate is staying constant throughout life. So, this by the mortality angle, this is not a aging population, right. Now, let us think in terms of numbers, and for the sake of calculation, let us assume that we have started our population with 100 individuals. Okay. So, 100 individuals, the mortality rate of going to the next age class is 0.1. So, how many individuals will I have? 100. So, basically this number equal to this number minus 10% into this number again, right. So, 100 minus 10% of 100 is 90. So, what will happen in the next generation? 90 minus 10% of 90, which is 9. So, 90 minus 9 is 81, and we can click on this and you can see it will go on. Now, obviously, in a real population, biological population, these numbers will not be in decimal, but we are doing a simulation, so we will just let it be. The other thing to note is that since we are reducing the population size by 10% every generation, this will keep on happening forever. The number will become smaller and smaller, never really hitting 0. But for the sake of our simulation, we will assume that once it goes below 1, which is at this point, I will increase the size slightly, which is at this point we will assume that the population size has hit 0. Okay. So, arbitrarily we will make the population size 0 at this point, and we will delete everything else. Again, as you will see, this does not really affect our final outcome in any way. This is just for the sake of calculation, right. So, now we need to compute what is the survivorship for each age class. So, the survivorship in technical language is also denoted by the letter L, and we are calling it Lx, means for that age class. So, here we have all of them surviving. So, equal to this number by 100, which is 1. Here 90 out of 100 are surviving. So, equal to, and I will just drag this. So, 90 out of 100 are surviving. So, this is 90 out of 100, 90 by 100 0.9, 81 out of 100 are surviving. So, 0.81 and so on and so forth. Great. Now, look at the fact that this particular survivorship value, Lx value, is also telling us something else. What is that? It is also telling us what is the probability of any randomly picked individual from this group at the beginning, what is the probability that it will survive to that age class. So, for example, here this is saying is that the probability that a randomly picked individual will survive to age class 2 is 0.81. Now, many students find this very intuitive, they are able to get it like this. For many students, this transition, why the survivorship is the probability, many students find it a little difficult. So, think about it this way. Assume that these 100 individuals, these 100 newborns that we had right at the beginning, let us assume that all the ones that are going to live to the next age class, let us say we color all of them black, and let us assume that the ones which will die, 10% of them, those we color them as red. Okay. Now, we want to ask what is the probability of a randomly selected individual to survive to the next generation, to the next age class, right. And so, for this one, and that question can essentially be translated into, if I put my hand and select a random individual from all the newborns right at the beginning, what is the probability that I will pick a black individual, because black individuals are the ones that will survive, right. So, that probability is obviously 90 out of 100, which is 0.9, and in that way this number also gives us the probability of a given of a randomly picked individual surviving up to that age class, right. Now, let us take reproduction at age class x, okay, and reproduction at x, and this is typically denoted as mx. Okay. So, let us assume again for the sake of our simulation that right at the beginning of their life, right when they are newborn, they are able to produce babies, and let us assume that they are producing at the rate of 2 babies throughout their life at all age classes. Again, remember the definitions of aging, the evolutionary definition of aging suggests that the reproduction towards the later part of the life should go down, but here we are explicitly assuming that it is the same throughout their life, which means again by the reproductive criteria as well, we are assuming that this is a non-aging population. Okay. So, this is how many babies that they are producing. Now, we come to the second postulate that we had made. What is the second postulate or second observation, which was that in order for an organism to reproduce at a certain age class, it will first need to survive up to that age class. If it cannot survive, then it cannot reproduce, right. Therefore, if we are to understand that on an average how many babies an individual is expected to produce at a given age class, then we need to multiply the number of babies produced at that age class with the probability of surviving up to that age class, right. So, this is what is known as the reproductive success for x. Okay, I will just put it above reproductive success for age class x, and this is simply Lx into mx, okay, equal to Lx into mx, and we will click on this and there we go, right. Now, note here that because this mortality rate is, there is a finite mortality rate at all age classes, therefore, the overall survivorship across the age classes, that has to be a decreasing function. Okay. There is no age class at which this is going to be equal to 0, and therefore, this will be monotonically declining. However, the same is not true for LXMX. Why that is so? In this particular case, we have assumed that all the values are the same, but we can get situations where let us say later in life an organism starts producing more number of babies, right, and that happens all the time. I mean, take humans for example. We do not produce any babies for the first 12 to 15 years of life, but then we start producing babies and then we can produce babies at roughly the constant rate for a long time. If you look at Drosophila for example, first day of its life it can't produce any babies, then it produces lots of eggs and then the reproduction comes down and then it remains constant for some time and then it slowly peters out over its entire lifetime. So, basically different organisms will produce different number of babies at different points in its life, and therefore, it is entirely possible that this reproductive success thing that we are computing Lx into mx, this need not necessarily be a monotonically declining function, it can have a peak somewhere in the middle. So, in the context of this non-aging population, however, it is going to be a monotonically declining thing. Now, think about what each one of these numbers are telling. Each one of them are telling that what is the expected number of babies that the organism will produce if it ends up surviving to that age class. So, now if I were to ask what is the total number of babies that an organism is supposed to produce over its entire lifetime, that is simply going to be the sum of all these values, right. So, let us do that sum. That sum is this, right. So, this is the expected number of babies that the organism should produce over its entire lifetime, right. So, now we are going to quickly compute two other quantities. One is what is the cumulative reproductive success. What is that? That is simply how many babies are it producing cumulatively as it goes over time. So, this in order to compute this this is at step 1 it is 2 and at step 2 this is equal to this plus this. So, 2 plus 1.8 3.8. Similarly, at the next step it will be 3.8 plus 1.62 which is 5.42. I click on this and I get the entire cumulation. Not surprisingly, the last value over here is this value over here, right. And now, this is just for the sake of plotting, we will also do this in terms of percentage, right. So, what percentage of its lifetime reproductive success does the organism achieve by a certain age? So, in order to do that, what we will do is we will take this value and we will divide it by this sum over here, and this sum we need to put in $2 over here to ensure that it is only dividing, the denominator is only this value and nothing else. So, that gives me the ratio, and now I multiply it by 100 and I get the cumulative percentage. I click on this and of course, it ends up at being 100. Excellent. So, now that I have all the figures that I wanted to look at, now I am going to draw some plots. The first plot I will draw is that of survivorship, and I go to insert, I look at charts and there you go. Okay. As you can see, the survivorship is monotonically declining, but what you should also be able to see that it is declining at a pace much faster than linear, it is actually exponentially declining. Great. What is the second graph that I will draw? The second graph that I will draw will be this reproductive success thing. I will just call it LXMX over here, or repro success LXMX. So, this is the reproductive success. As I said, it is monotonic in this particular situation because of the fact that we have taken two individuals at all age classes. If you have higher reproduction in the middle, then this can have a peak. So, let me just show you. For example, let us say I make this one value as 20. You can see it is having a bump over here. Suppose I make the next value 18, you can see that the bump is nice bump is happening and so on, right. Anyway, so this is the reproductive success LXMX, and the third one that we will look at is this one, the cumulative percentage. And what is the cumulative percentage graph looking like? The cumulative percentage graph is going to look like this, right. Essentially what this is saying is that even though in this particular case my organism lives for 43 years, even though it lives for 43 years, the value reproductive success over its lifetime comes very close to 100 much earlier than it's 43. So, in this particular case, for example, let us just look at it, where does it hit about 90%? It hits 90% at about age of 20, right, and the remaining 24 years it is just getting 10%. Now, let us reduce the size a bit further. Yeah, so here are our 3 graphs, and with these 3 graphs now we are in a position to understand what is the crux of the evolutionary theory of aging. So, let us go back to our PPT for that. So, yeah, these are the 3 graphs that we saw. Now, think about it. How does natural selection operate against, let us say, a mutation? Natural selection operates by reducing the fitness of the organism. In what form? In this particular case, it is going to be the number of babies, or it is going to be the lifetime reproductive success, that sum that we took, right. Now, if you look at that sum and if you look at the how various ages are contributing to it, you see that there is a huge discrepancy between the contribution from the earlier ages and the contribution from the later ages. So, if you look at here, you can see that the earlier ages are contributing much more, the later ages are contributing much less, which is what you can also see from this cumulative reproductive success. In the initial part, the cumulative reproductive success is increasing steeply, but in the later part of the life it is actually becoming very, very flat. So, suppose you have a mutation, and that mutation, let us say it is causing some harm, okay, it is causing some lack of fitness. Now, that harm, let us assume that is being caused early in life. In other words, it is reducing reproduction slightly early in life. In that case, the way it will hit the organism's overall reproductive success is much greater. Okay. So, any reduction in survivorship or reproduction early in life is going to play a role in this part of the curve, and which means that natural selection is going to be very effective in favoring or weeding out, if it is bad, any mutation in the early part of life. But suppose now you have a mutation which is affecting the organism only later in its life. So, even if the organism, even if that particular mutation is, let us say, reducing reproduction to 0, or even if it is killing off the organism and making your LX very, very less, even then the overall contribution to the reproductive success of that part is going to be very less, because of which natural selection is hardly going to be of any major effect. So, that is what we mean by saying effect of natural selection goes down with age, and late life deleterious mutations, they are typically much less affected by selection. This is what is in technical term known as selection shadow. So, I will just take you to this demonstration one more time to show this. So, just to show this to you numerically, suppose okay, let me do one thing, let me get this let me get this sum over here, okay, equal to sum this cumulative reproductive success, let me get this sum, sorry, this reproductive success, let me get this sum right here. Okay. This is that same 19.806 value that you saw. Now, let us assume that there is a mutation which is affecting early in life, and because of that mutation, let us assume that this reproductive success in the first 2 years is becoming 0. Okay. So, let us do that. What is happening? Just by affecting the reproductive success in the first 2 years, from 19 point something you have gone to 16 point something, right. That is quite a huge reduction. But suppose now we do the same thing late in life, let us say we do it here, we make this 0 and we again make this 0. From 19.86 you have gone to 19.76, just a 0.1 difference, right. So, this is what we mean by saying that the deleterious effect of a mutation that occurs earlier in life is far greater in terms of the overall reproductive success than the deleterious effect of a mutation that happens much later in life. And because natural selection operates by making differences in the reproductive success, overall reproductive success, therefore, even if there is a slight change in this thing, natural selection will not be able to weed it out, or it will be much less effective in weeding it out if the deleterious effect is expressed later in life as compared to if the deleterious effect is expressed earlier in life. This is the crux. Okay. Not all mutations are same. Early acting mutations are worse in terms of affecting an individual's reproduction, overall reproductive success compared to late acting mutations, and this is what leads to this concept of selection shadow. Now, of course, one has to ask that does it really work? What does data tell us about the effects of selection shadow? How big is this effect? So, that is what we are going to look at in our next discussion. Thank you.